The next stressor we want to look at is volume. So if we change the volume of a system at equilibrium, will it have an impact? Will anything change? So let's consider this example. For this reaction, at equilibrium, the following is true. So here is its expression for the reaction quotient, which happens to be equal to K because it's at equilibrium. Now, if the volume that this equilibrium mixture takes place in is decreased by a factor of 3, the partial pressure will increase by that same factor of 3. And going back, right, the reason for this is going back to our ideal gas law. We see that pressure and volume are indirectly proportional to one another. So let's actually take this factor, this change of 3 into account in our reaction quotient. So this is the reaction quotient at equilibrium. If we increase the partial pressure by a factor of 3, we would just multiply our pressure of our products and reactants by 3. So I have 3 times our reactant, 3 times our product over 3 times each reactant. So that will simplify to, so this is actually 3 squared. This is 3 squared because of this coefficient 2 in front of our product. It's how I have it written, it may not be clear, right? So imagine we put 3 inside of the parentheses. So it should be 3 times the partial pressure of hydrogen iodide squared. So that's how we end up with this 9 here. We multiply 3 and 3, we have 9. So it reduces back to our reaction quotient Q, back to Q sub P, the same as what it is at equilibrium. So in this case, changing the volume does not result in a shift in equilibrium, right? Because our Q reduces back to what it is at equilibrium. So let's look at another example to see if this is universal, if this is universally true. So here's another example. Here's another example where we have 2NO2 decomposing to nitric oxide and oxygen gas. So here is the reaction quotient at equilibrium, right? It will be equal to K. We have reactants over products raised to their coefficients. Now, same example, if we change this volume by decreasing it by a factor of 3, thereby increasing the partial pressure by a factor of 3, how will this change Q sub P? So it turns out, right, when we do the math, so we multiply each product and each reactant by 3, so we end up with, and you can go through in detail with the math, but we end up with basically 3 times Q sub P at equilibrium. 3 times Q sub P. And actually, let's go through the math. Let's go through the math together. So 3 times the partial pressure of product NO, and it's raised to a power of 2 because of our coefficient of 2. So we end up squaring that. So we end up with 9, and then we still have the partial pressure squared of NO. We multiply 3 times the partial pressure of oxygen gas. That has a coefficient of 1, so we just have that 3 still there. For NO2, we square it because we have that coefficient of 2, so we pull out the 9 and we have partial pressure of NO2 squared left. Now we multiply our 9 and 3 together to get 27, and then when we divide 27 by 9, we end up with 3. If we just look at this part minus the 3, notice it looks identical to Q sub P. So Increasing the partial pressure by a factor of 3 results in increasing Q sub P by that same factor of 3. So because we increase Q sub P, it's greater than K at equilibrium. So in this case, right, when we have Q is greater than K, our equilibrium will shift to the left. It will shift to the left. So in this case, changing the volume does result in a shift in equilibrium to the left. Now, before we summarize why we see that for this reaction and not the other one, let's look at the total molar amount. So let me go back. Let me go back to that first reaction. So we had coefficient of 1 for hydrogen, 1 for iodide. So total molar amounts for reactants was 2. Total molar amounts for products was also 2. Now for the other example, we had total molar amount of reactants of 2 and total molar amounts of our products was 3, right? 2 for NO plus 1 for oxygen gas, 3. So the change in volume, whether or not changing the volume of our system has to do with the total molar amounts of reactants and products. So if they are equal, if the molar amounts of the reactants and the products are equal, as we saw in our hydrogen iodide reaction, then a change in the volume does not shift the equilibrium. But if the total molar amounts are different, which we saw in our second reaction, where we decompose, I think it was NO2, those molar amounts were different, so a change in the volume did shift the equilibrium, right, in the direction that'll better accommodate the volume change. So it did shift the equilibrium. So volume is a change in volume will shift the equilibrium, but it is dependent, or it may shift the equilibrium, and it, whether or not it does or doesn't, is dependent upon if the molar amounts of reactants and products are equal or different. So volume is a little different compared to, say, concentration or partial pressure.